Uh, Good morning and good afternoon to everyone. It's an absolute pleasure to be here today. My name is Tim Carstens. I'm a software engineer at a little ZK company called RISC Zero. And today I want to talk a little bit about what RISC Zero is, how it works, who's using it, and maybe we can then do some Q&A or whatever at the end. So we'll kind of start at the beginning. What is zero knowledge? And while preparing this talk, I had a few options as to where to go for the next slide. On the one hand, I could take it in the Dan Bonet direction and lay out verifier and approver and some complexity hypotheses, but let's actually try to keep it a little higher level. So for our purposes today, what is ZK? ZK is a new primitive for distributed compute. So mechanically, what it looks like is something like this. Up at the very top, we have Alice, and Alice is going to run a program. And she'll key in some inputs, the program will generate some output. And when the program is done producing its output, she's got some options for what she wants to do. She can take that output together with a zero knowledge proof and send it to Bob, who can then verify that proof. And he then concludes that the output really did come from that program. Or she can take the output and that proof and put it on chain. And a smart contract can do all the work that Bob just did and then take some action based on the outputs of the program. This is a very weird kind of thing. I've been working in the internet for a while now, and for the most part, when someone sends you something over the internet and tells you it came from some program, the only way that you can actually be sure of that is basically to rerun the computation yourself. With ZK, we skip that step. The idea is that when you run the program, you obtain not just the program's outputs, but you also obtain a proof that shows cryptographically that those outputs came from that program. Okay, so that's a weird thing, and it takes a little bit of time to sink in what you can do with that. So that's kind of what we're going to digest a bit here today. So at the very highest level, there's a few key properties of this process that makes it more than just theory. Everything I just described right here was theoretically possible in the 1980s. The Turing Award for these ideas was in the 1980s, right? But what makes it practical? Well, so one of the important features of ZK systems is that the inputs to these programs remains private, right? And so the idea is this program might ask, hey, Alice, type in your social security number, and then maybe it outputs the sum of the digits or something silly like this. She can prove that the program really did produce that output, and that proof does not reveal the inputs, right? And so it's expected and hoped that this will be useful in all sorts of applications. Shafi Goldwasser, one of the people who won the Turing Award for this work, is a professor at UC Berkeley, and she's working right now on applications to, for instance, document discovery in legal proceedings. So this is one of the key things. This is the zero knowledge property. The inputs to the program remain private. Another one of the key properties that makes all of this practical is that the proofs are small and easy to verify. Now, there's lots of different approaches to ZK, and they all have slightly different characteristics. When I say that the proofs are small, I mean that you can get them to be less than a kilobyte in size. And when I say that they're easy to verify, I mean consumer hardware can verify them in milliseconds, basically a time proportional to your ping time to Google, more or less, right? So the proofs are small, easy to verify. And in fact, they're small and easy to verify. This is shocking, but they're small and easy to verify regardless of how much compute they're proving. This is sort of the most amazing thing about these systems, and it's what allows them to scale. Another key property is that the proofs cannot be forged. Now, if I was doing the Stanford cryptography talk, I'd have to put some asterisks on here. Technically, an adversary with infinite compute can forge these things because it's just a cryptographic system. They can brute force it. But there's hard analysis on the complexity of these things that indicates that doing so is essentially impossible. We're talking about levels of difficulty that are comparable to inverting hash functions. And then lastly, all of this works on consumer hardware. You don't need to have a supercomputer. You don't need to have a terabyte of RAM. You can do it on your MacBook just fine. If they're smaller programs, you can do it on your mobile device or in the browser. So this is kind of the basic lay of the land for the main characteristics of these systems. So that's like what it is. Letting it sink in a little bit, there's many different ways to think about such a compute primitive, right? Many different ways. So I listed just a few examples here that all speak to different perspectives on how to do engineering with ZK. So, kind of the day one sort of mental model is that ZK gives you a method for proving that some data was generated by a particular program without revealing the inputs to that program. That's kind of the definition I just gave previously. But another way to think about it more purposefully would be to say that it's a way to prove claims about private data, right? I can prove properties of any data, of any of these inputs, by just running a decision procedure that would recognize those properties and then sharing the output of that proof with you. For the cryptographically minded, another way of thinking about ZK is that it's a broad generalization of the concept of a digital signature. Traditional digital signatures, I think first publicly conceived of by RSA and first privately conceived of in government by a guy named Cook working in the UK. Original digital signatures, the idea is that you use this public key cryptography. Users have a private key that they can use to sign data, right? And so in this sense, it generalizes the concept of a person signing a document, right? Well, the ZK stuff takes it a step further. With ZK, you can think of it as though programs are signing their own outputs simply by virtue of running. There's no private keys involved. The user doesn't have a private key. There's no private key material anywhere. The program can be completely open source, and yet magically, it's not magic, algebraically, what happens is essentially the program has signed that its output came from it just by running. Totally wild idea. Incidentally, you can use that to build an actual traditional digital signature scheme that doesn't use public key cryptography. And Starkware and RISC Zero both have an example of this where we each take a hash function and upgrade it to a post-quantum digital signature scheme. Totally wild stuff. And then lastly, and I think that this is the killer app for blockchain, ZK is a way to reduce redundant computation in adversarial environments, right? You have this blockchain, you've got hundreds of thousands of nodes burning however much electricity or sitting idle in a data center because it's a proof of stake system, either which way. The idea here is that instead of having to check each other's work by rerunning the computation, the way that Bitcoin works, for instance, these nodes could in fact just prove that they ran the algorithm defined by the protocol and just share the result with each other. And then they just have to verify that result. And this is amazing for chain scaling and such because, of course, these proofs, they're constant size, regardless of how much compute they are attesting to, which is not something that's true of, say, rerunning all the computations every single time. So there's lots and lots and lots of ways to think about what ZK does for you. So what is RISC Zero? All right. So RISC Zero, our thesis is that we're here to make ZK easy. So not long ago, say 2 years ago, if you wanted to get into the ZK game, you would maybe check out some of the work by Xerox PARC. Maybe you would play around with Circom a bit. Maybe you would grab the tooling from Starkware, write a little code in Cairo. A few different options, all of which we're going to challenge you and your team to learn some new languages and tooling. And because they're new languages and new tools, probably have to write a bunch of your own libraries. And it really stacks up to being a lot of work. What we do differently is we say, let's do ZK, but let's make the programmer's experience as familiar as possible to just writing ordinary software. So we said, let's lean into existing standards, especially for programming languages, but also for crypto tech. And let's bundle it all up in a way that's just going to integrate really smoothly with your build tools, your CI, your deployment story, the whole 9 yards. So the way that we achieve this is that we provide ZK tooling that you can basically think of as being just a virtual machine. And that virtual machine provides completely standard RISC-V CPU core, RV32IM in particular, together with various accelerated hardware circuits for specific crypto tasks, like say SHA hashing, which incidentally is exactly how your desktop processor works. You have a general purpose processor, and it literally does have little side circuits for doing all the popular SHA, SHA, AES, et cetera, so forth. So because we provide that, if you're a person looking to build a ZK app, you don't need to be a specialist in any of that stuff any more than you do if you're writing software for Mac OS or Linux, right? All you do is you create a Rust project. We recommend Rust for reasons. Happy to talk about them. But you create a Rust project, and you just write your code. You bring in existing libraries. You just use them, right? How many libraries are there for Rust? Plenty. There's enough, especially if you're in blockchain. Rust has become super popular. So the example that I have here on screen, we don't need to walk through it line by line, but on the left, I have an example of a program that runs inside the RISC Zero stack, inside our ZK VM. And this program is just checking to see if a 256-bit integer is even or odd. And by design, it's only willing to output even numbers. So if you pass it an odd number, it'll flip a bit and make it even, right? So this is kind of a way to ZK prove that a number is even. And by itself, that sounds probably kind of boring. But if you take a look at the library imports at the very top, you'll see that we're bringing in libraries from a Rust crate called Alloy. And this is where the value of being in the Rust ecosystem really kicks in. Alloy is a stack of crates, Rust libraries if you're not a Rust programmer, that provide basically an implementation of everything you need if you're going to do anything with Ethereum. So they give you the ability to parse and run Solidity. They give you an implementation of the EVM. You get like all this great stuff. And so here in this program, I'm actually reading in a 256-bit number. Here I'm thinking to myself Ethereum integer. And then the output is actually the Ethereum ABI encoding of that integer. Because it outputs in that format, it'll be easy to read on Ethereum, right? So if you were doing this in another stack, you would have to hope that the Ethereum ABI encoding libraries had already been written by someone. And if not, congratulations, you have a new subtask. You have to like do RLP, you have to like figure out all that stuff, figure out how the packing works, deal with the zeros. There's like all these little edge cases. You got to, you know, good news, your project just got longer by a few weeks, right? So that's kind of what the guest looks like right there. And it's pretty typical of guests. These guest programs that run in the VM. And then on the right-hand side, I have an example of how to actually run this program and generate a proof. And again, it's written in Rust. But the procedure is really straightforward. You know, we have some logic that sets up the environment the VM will run in, including the inputs to the program. We then say, hey, give me an instance of a prover object. There's a few of them that you can use. You can use one that runs locally on your computer. There's another one that runs on a giant cluster that we operate in the cloud, depending on, super useful if you want to do a giant proof quickly. Anyway, it kicks that off, fetches the proof. We call it a receipt. Checks the receipt and decodes the output, right? So this is kind of the standard pattern for these things. And incidentally, because it's in Rust, it may as well be in JavaScript or TypeScript or anything else, because the tooling to go from Rust to WASM is super good. And so if you want, you can take this program. Obviously, you can run it on Linux, Windows, Mac OS. But you can also run it in browser just fine through the Rust WASM gen tooling, including the proof verification. Runs in the browser, lickety-split, no problem. Or if you're in a, say, COSM WASM environment, still no problem. You can WASM gen this thing. It'll absolutely run just fine. No fancy code is emitted. So I'm an engineer, but when I give a talk please go ahead.
Just a question on the Rust support. So do you support like the standard library for Rust?
Absolutely. Great question. And yes, we do support the standard library for Rust. Now, there's some important caveats to that. The Rust standard library, like most language standard libraries, includes a bunch of functions that don't necessarily make sense in a ZK context, right? And so, for instance, get time of day. There's no way to prove what time it is in ZK. So you can make the call, and with a certain mode enabled on the VM, it'll ask the host what time it is, but there's no way to prove that. Nonetheless, the call will work. Importantly, though, because STD is present, all of the things that do make sense in ZK, they are implemented, which is most of the standard library. And so this makes it easy to just grab existing Rust crates and just use them as is with no changes. And in fact, I think we have a leaderboard where we track the 1,000 most popular Rust crates, and we build them in our environment. We run some basic tests, and I think that we're compatible with more than 97% of them out of the box. And the things that we're not compatible with tend to be things that, for instance, require symmetric multiprocessing or other kind of advanced threading stories or things like that, or which have embedded assembly. So the kind of things that logically wouldn't be in our VM, right?
Makes sense.
So this is the shill slide. So I'm going to move through this fairly quickly because this is a tech talk and not a sales talk. But it does give a sense of, what kind of things we've put most of our work into in our stack. So our premier thing is this VM that runs these Rust programs and generates these proofs. We call it the ZK VM. It was the only ZK VM when we released it. Now ZK VM has become kind of this category of tools. We're the first to adopt a general purpose instruction set architecture, the first to adopt RISC-V. It's funny, when I mention this now, people just shrug and say, yeah, it makes perfect sense. But the first times I gave a version of this talk, like a year and a half ago, we were brand new, people hadn't tried us out yet. Everyone was telling me it would never work. So it just really speaks to the progression of the technology here and how fast the impossible has become possible. Our VM was the first to support this thing that we call continuations. The idea here is continuation is a feature that lets you run arbitrarily long computations in ZK. And if you're just a regular programmer, you might think to yourself, isn't that normally how programs run? They run for as long as they run. And the answer is, yeah, if you're writing software. But in ZK, before we released continuations, all of the platforms had a limitation on how much compute you could do within a single proof. The circuit paradigm is not Turing complete, for example. And so anytime you were writing circuits, there were limitations there. And then the other VMs, Delphinius, Starkware VM, etc., all had limitations imposed by cryptographic parameters, essentially, on how much compute. So we launched this feature called continuations that allows you to just not worry about fitting within these tight limitations. It just runs your program for as long as it needs to. To generate the proof, it actually has this feature that takes the chunks for that work, for the proving, and actually splits it up, does all the proving in parallel, rolls them all up for you super fast. We'll talk about it more in a little bit. We have one of the cheapest on-chain verification costs. I think it's 270,000 gas. We're currently testing on Sepolia with deployment to Ethereum coming up probably next quarter. And then lastly, the VM runs on consumer hardware. A lot of the ZK tech requires more than 500 gigs of RAM. That's cool. I'm a principal engineer. If I ask for a half terabyte of RAM, they'll give it to me. But most people do not have access to that much memory. Certainly not most crypto end users. So we really wanted to focus on consumer grade hardware. Apple M1, M2, M3, NVIDIA CUDA running on 3080, 3090, 4080, 4090, that kind of environment. Is proving compute heavy? It is, but it's actually bounded by hash throughput rather than being bounded by memory. And this is part of what allows it to work in parallel super effectively. Let's see. So the other main thing that we like to focus on is, again, that smooth developer experience. Our entire stack is open source. It's Rust first, but it's RISC-V, so really any language that you can compile to RISC-V is totally happy. I come from a security background, so I really push that Rust card pretty hard. As far as the security of the system is concerned, RISC Zero has, as far as I know, the highest security guarantees, audited guarantees of any of the ZK VMs. By Starkware's metrics, I think that we're around 80 bits of security today. And we are pushing towards exceeding 100 bits of what's called proven security in the ZK space to happen this year. So we're not achieving performance by sacking security. We're looking for the highest standard there. And then as far as on the really nerdy side of things for the crypto hypotheses, our system is fundamentally Stark based, and our Stark implementation is entirely based on classical crypto features, in particular hash functions. And so our security guarantees boil down to the security of hash functions. This is unlike many other ZK systems where the security hypothesis includes more recent security models such as bilinear discrete log or other kind of elliptic curve motivated things. Although, of course, we also support conversion to Snark for on-chain verification, and that does use elliptic curves. Audits have been completed. We're in the midst of fixing the findings from that. None of them were critical. And those audits were extensive. I think we had 3 or 4 different teams of specialists working on on different and overlapping parts of the system. And then lastly, for folks who do want to prove truly enormous computations, we provide a cloud service called Bonsai that will spin up hundreds of GPUs to work in parallel if you have a really large proof that you want to get done rapidly. For instance, maybe a fraud proof on a large chain or something of that sort. And this is the kind of thing that can get that to you in minutes. So I already alluded a little bit to how the system works. This one slide here could easily be a series of talks. I like to tell folks that, you know, if you like computer science, you'll like working at RISC Zero. There's an awful lot of ideas being put to work in order to build this system. Kind of naively, you think, oh, I'm going to build a ZK VM. All I need to do is write some circuits, and then I'm done. And it's like, yeah, that's the first 90%. But then you got to tackle the other 90% of making it fast, usable, stable, all secure, all these things. So what we did at RISC Zero is we started by building a ZK framework around Starks. And there, in contrast to other teams, we really wanted to focus on the proving performance while selecting the parameters in our Stark framework. What do I mean when I say in contrast to other teams? Well, if you set out and the only thing you care about is Ethereum, like you really, really want to do a ZK EVM, then you'll take a look at the Ethereum virtual machine. You'll say, I need 256-bit words, which is wild, but it's what they picked. And so maybe you think to yourself, I need ZK to be super efficient on words of that size, 1/4 of a kilobyte. And so it's not 1/4 of a kilobyte, my bad, but whatever, 32 bytes. You know, so you say, okay, I'm going to go ahead and optimize around that. Well, if you start baking that into your Stark system, it's true that you will get good performance for those large words, but it's also true that you're going to have bad performance for proving on any kind of modern hardware, because modern hardware doesn't have 32-byte words, right? On GPU, you get like 32-bit words. So we really picked, you know, parameters that were going to be optimized for the actual performance and said, we know how to do multi-lim arithmetic for the larger word sizes. I promise I'll go through the other points faster. I could really get stuck here. So anyway, we set up a really efficient Stark framework. We then sat down and built kind of a pseudo-functional language for doing circuit descriptions targeted towards our proof framework. Couldn't use CIRCOM, couldn't use any of the other things designed for R1CS. We are not working in the R1CS paradigm, so we built our own language for all of that. And then we used that language to implement a variety of ZK circuits that work together to provide this ZK VM experience. So how are people actually using it? What are some things you can actually do with, you know, technology is fun, but if you never actually use it, then it doesn't count, right? So I think that probably the projects that we're best known for all stem out of this project that I worked on last year. I guess I still work on a little bit, called Zeth. So the idea with Zeth is we were taking a look at the ZK landscape, and we said, man, there sure are a lot of teams working on a ZK EVM of one kind or another. Vitalik wrote this famous blog post called The Different Types of ZK EVMs, and I took a graphic from there that we adapted and included on the slide. And you can see that this time last year, the problem of building a ZK EVM was basically at the cutting edge of what's possible. You could go to Sequoia and raise $200 million, go on a long acquisition spree, build a massive team, and just throw as much as you can possibly at it, and still wind up with a ZK EVM that's not quite 100% Ethereum compatible, right? This was the state of play, and we've seen a number of companies go exactly that route. So one of the questions that we asked ourselves last summer was, could you build a ZK EVM on top of RISC Zero just in kind of the naive way, right? We have the ability to run arbitrary Rust code. There are Rust implementations of the EVM and everything else you need to build an Ethereum node. Let's just try running it and see what happens, right? So that's a project called Zeth. And the results, if I'm being honest, they actually surprised me how well it worked. It basically took myself and two of my colleagues about 3 weeks to have an example up and running that was able to process full Ethereum blocks, execute all their transactions, update the state roots, verify the digital signatures, the whole 9 yards. 3 weeks of time. And I'll mention, I'm not an expert in Ethereum. In fact, when I started on that project, at that time, I'd never done anything with Solidity. I'd never had an Ethereum wallet. I'd never had a MetaMask plugin installed. I was an old Bitcoin guy, right? So I'm sort of the least likely person you would pick to work on something like a ZK EVM. And yet, because of RISC Zero, 3 weeks. 3 weeks, we got it up and running. So that's out there. That's open source. And since then, a number of teams have started building on it or doing other experiments with it. And so some of the work that we're well known for is we have a project with Optimism right now. So does O1 Labs. They're another team in this. And we're basically taking the Optimism fraud-proof mechanism from Canon, the old Canon design, and we're modernizing it with ZK. And so for this, we said this should be pretty straightforward. The whole point of fraud proofs and Optimism is, someone posts essentially a new state root to the L1 and it's wrong, and you need to convince everyone else that it's wrong. Well, one easy way to convince everyone that that value is wrong is to prove to them what the right value is, right? So we said, okay, let's take Zeth, let's modify it so it works for OP blocks, and let's see how long that takes. And the answer is that took like a week, right? Because Optimism is basically super, super duper close to just being Ethereum. And the crates that we were using to implement our Ethereum support also supported Optimism. Okay, so that was easy, right? Another team, Tycho, at this time was in a collaboration with the Ethereum Foundation. They were working on building a Type 1 ZK EVM. They were building circuits for it. They've been working on it for a couple of years. And when we released Zeth, they called me out and said, well, thanks. We're done with that. We can just use Zeth, I guess. And I said, yes, you can, right? It's completely open source. You don't need to pay us a dime to use it. And so today, in fact, that is what they are doing. And they have their own client called Ryko. That is a fork of Zeth, and they've added some features to allow it to run in other environments as well. But they found that it was sufficiently valuable that they, as far as I know, abandoned their previous circuit work and started switching over to this, lower friction, just use Rust, write your program kind of approach. And then unrelated to Zeth, we've also been collaborating with a team called Eclipse. And Eclipse is interested in doing basically a ZK Solana VM. And so they did pretty much what I did for Ethereum, right? They said, great, we'll take the Solana VM. There's an implementation in Rust. We'll just adapt it to run inside the RISC Zero VM. And now, all of a sudden, you have a ZK Solana VM. Super easy. Another team that's doing some really interesting work is Alware. So Alware is a decentralized sequencer platform. They provide a roll-up framework and a roll-up as a service type offering. And they wanted to make it easier for their users to embrace ZK fraud proofs. And so here, again, kind of an extension of the types of ideas that we just talked about for Optimism. Here, the idea is like, you can design a very complicated fraud-proof protocol, or you can design a really simple one that uses ZK, right? The former is like Princeton graduate work level stuff, right? I mean, that's where Arbitrum came from, is, Center for Information Technology Policy at Princeton. If you are a professor and you have 7 years to ideate, great, design your own fraud-proof system. But if you're looking to get to market and compete in this fast-moving place, just write it in Rust. Just move on with your life. One of the cool things about Alware is that they basically were able to go from idea to a proof of concept in under 2 months with no whole hand holding from RISC Zero. They basically just showed up and were like, hey, we tried this thing out, it just worked, and it blew our minds, right? And then there's a few other partners who are working on some stuff. I'm allowed to mention what they're working on, but they're stealthy enough that I can't say who they are just yet. A leading staking and restaking protocol is doing a project right now to reduce their gas costs by more than 90% by offloading compute into RISC Zero. You can imagine that they have policies on when you're able to withdraw. And these policies you can check them on Ethereum, but it's expensive to do so. And so you can get these huge savings by just doing a ZK proof that shows that your request is valid and lawful. And even the cost of verifying that proof is actually lower than the cost of running the computation naively on Ethereum. Another example, there's a prominent DEX that we're working with. A lot of folks in the DEX space have been frustrated for years and years and years by the state of, what's possible with decentralized exchanges, right? I myself am still waiting for the GOX reimbursement, so I've known that pain for 10 years now. And there's for years there's been this promise of we'll have these high volume exchanges, they'll be decentralized, just as good as Coinbase or anyone else, but zero risk of getting rugged, right? Oh my God, wouldn't that be wonderful? Why has no one built it yet? Well, it's because the blockchains don't scale to supporting an interesting volume of transactions, right? And so what this company is doing is they're saying, okay, great, we'll just do the whole thing in ZK. We'll make sure the data is available via, say, Celestia, and we'll just run these expensive order book matching algorithms inside the ZKVM and just at settlement time prove that the settlement instructions were the output of the matching algorithm, right? And then sort of the last interesting kind of new application area that we're working with a few different companies on concerns identity integration. So every tech worker knows that basically half of your job is just logging into websites throughout the day that, reset your credentials every week or whatever. And, the big solution in the web for that was single sign-on, OIDC, OpenID Connect, and technologies like that. So we wanted to bring those technologies to the chain. And in order to do that, you have to be able to do a bunch of expensive cryptographic operations somewhere. You don't want to do them directly on chain because no one can afford to be the only transaction in a block. And so instead, you do the crypto checking, like the certificate checking, the token checking, do all that logic inside the ZKVM, where it's actually really easy to, because there's tons of Rust libraries that know how to integrate with these identity providers. And you just do the obvious thing. The user logs in, you feed in their token into the ZKVM, do some certificate checks, output that, yeah, they're bona fide. So we've shown that this works with Google. We did a demonstration at the end of last year. Hundreds of Ethereum users sent and received ETH to each other using your Gmail address. We have an integration with ID.me if you wanted to, say, verify that someone's a US citizen or double check their social or their address or any of these kind of super personal data. If you integrate with Apple, Apple's OIDC provider has a machine learning model that tells you if they think the person's a real person or if they're a bot. Like, that's actually kind of useful. So there's a lot of these interesting kinds of things that are achievable when you can just grab the Rust library that implements all the stuff, run it in the VM, post proof on chain. So lots of exciting things are taking place right now. We're still at the beginning of the ZK journey. The kind of performance that we have today, I think, is we're all going to be laughing about 5 years from now. The performance is still just getting better and better. So the big question for everyone here is, what do you want to build? Thank you.
Thank you, Tim. That was awesome. I think we have some time left, so if anyone has any questions, just hop along.
I think you mentioned like CosmWasm earlier. Like, is there already like a repo that supports CosmWasm? But
yes,
Zero?
Yes. We're working on it right now. I'm scratching my beard because I'm trying to remember if we've marked it public yet or not. But in fact, actually, so we've been talking to James from your end, and he had suggested exactly this idea. Like, RISC Zero shows how to verify the proofs from within the CosmWasm environment. Let's do a demonstration involving that. So my colleague, Austin Abel, who's actually on, our companies have a Slack bridge, so you can reach him there, has a demonstration of this in action. I'm lucky he knows a lot about the CosmWasm environment. And I think that the plan is that we want to do a test deployment. So I understand you guys are working on a test net coming up here soon. So we're going to take a look at that.
Yep. Awesome.
Tim, can you speak a little bit when Polygon announced their Type 1 prover, right? They came right at RISC Zero. A lot of comparisons. Can you unpack that, like, from your view, what you thought was accurate, and just help us kind of understand what you read when you see that?
Yeah. So if I'm being honest, so first of all, I think that, like, rationally I should be scared, I suppose, right? Polygon is a colossal company, extremely well capitalized. And it's kind of scary being like the tiny guy getting called out by the big guy. But honestly, more than anything else, I'm just excited. when we started the Zeth project last summer, I did this write-up about its performance. I logged into our AWS console. I grabbed all the raw numbers. I was like, what instances are we on? How much time are we spending? What are we paying for these things? And I said, we're just going to let it all hang out. We're just going to be transparent about all of this because everyone, I'm here to talk to engineers. It's generally my role. And engineers just don't respect bullshit. So I was like, we'll just be super open about it. So I wrote this up. And the main feedback I got from people was, why don't we compare to the performance from, Polygon's, at the time it was not type 1. Why don't we compare to Polygon's performance? And the answer was, Polygon didn't share enough data to make that possible. And I reached out a few different angles. I reached out through some VCs. I was like, what can you get me? I just want to make some kind of comparison. And people would kind of whisper some numbers to me, but no one was willing to go on the record. And at the time, I was actually really frustrated by this because I didn't know, where do these systems compare for real, right? So fast forward now, it's been, 5-6 months, something like. And Polygon, when I read their announcement, it very much is a response to the write-up that we did back in September. They call out the direct comparison on the instance classes. They share a lot more about cost. They still didn't get into as much detail, but very close, right? Certainly enough to make a comparison. And so, being perfectly honest, I really felt like we had accomplished something by getting them to be more open, if you will, right? My friends and I sat down, we did a 3-week project, and the result is that one of the largest companies in crypto spun up a 6-month project. And I think that's neat. I think that's an example of competition working out well for users in this space, and competitors basically keeping each other on their toes. So that's all the exciting stuff. Now, as for the performance claims that they make, I'm inclined to believe them. They say that they're around 10x faster than us, and I hope so. I guess is my only answer, right? Ultimately, we're comparing a program where we just grabbed some off-the-shelf libraries and ran them to an ensemble of optimized circuits written by some of the best ZK researchers in the world. And one would hope that Polygon would get something for that extra effort and investment. And it turns out that what they get for all of that is a 10x speed up. 10x is no joke, but I imagine that the cost to build that was significantly more than 10x of our approach. So I'm still feeling very confident by the value proposition of enabling developers to just get things to market quickly. Let them write code in Rust. Let them get it out there. It's true that you will never achieve the theoretically ideal performance that way. Same as you don't when you write regular software on your computer, right? You can always go faster by writing an assembler or adding an FPGA. But in business, the key thing is that the cost has to be acceptable and the performance has to be acceptable. And importantly, you have to get market contact quickly. And I think that's that last one that's most important. And I still feel like our offering is leading in that way. That end, it's now our turn to respond with some additional accelerations.
Yeah, thank you. Very helpful.
Quick question on Bonsai. You touched on it briefly. What cases do you want or do you expect people to be using that? Like, is that going to be commonly used, do you think? Because I know it's you said it's like a proving service for more large scale projects.
Yeah, so we've actually got a pretty good spectrum of different kind of like loads that different users have been putting on it. So if you're doing proofs for like really simple programs, like earlier I showed a slide that showed like, let's check to see if a number is even or odd. That's something that you can prove on your laptop in like 7 seconds, right? You don't need a cloud service provider for those kind of simple checks. And in blockchain, most of the functions people care about are actually that simple. It's like, you want to check a signature scheme. It's too expensive to check directly on ETH. You can prove it locally on your laptop in a few seconds. Not a big deal. But there are some companies that are doing research in, say, ZKML, where they're interested in training and inferring from machine learning models in ZK. And there, the volume of data associated with those models by itself makes it impractical for the users to be holding those models and generating the proofs. And so there, having a cluster that can handle that much data in a proof and get you the result back rapidly because it's taking advantage of parallelism is just super convenient for people who are building, and it's convenient for the user since it keeps the latency low on getting the results back even for these large computes. So short answer, Bonsai is a SaaS offering, and personally I think it's most useful in pretty much the same use cases that SaaS always makes sense. You're trying to do a computation involving a ton of data, the computation's expected to run for a long time, like those kinds of things. That being said, there's also a few partners who use Bonsai even for super tiny proofs, just because they have a flow where the user goes to their website, initiates some action, and now their backend has to produce a proof and get it on chain. And if you're a backend engineer, that's like a whole extra pair of services you have to write. Or you can just call out to Bonsai and it'll just take care of it for you. So some folks use it for the massive scalability features. Other folks use it just because they need a way to generate and track what proofs have been generated, get them on chain, and why write that service yourself, right? I think I see some other hands. Kiana?
Yeah, no, you're on mute still if you're talking.
Oh, I just lowered my hand.
All good.
I wanted to ask, what are the biggest bottlenecks you would say you're facing right now in RISC Zero, irrelevant from like the broader ZK ecosystem?
I think the hardest thing generally right now is like really, I think we're feeling a lot of the same pain that a lot of infra providers in blockchain are feeling, which is that users want to build stuff that interoperates with a number of different kind of like chain-like architectures. The classic example would be you want to hold your state roots on Ethereum and make all your data available on Celestia, right? Like a few years ago, we saw the rise of this so-called modular thesis. Now we're there. A few years ago, we saw the rise of tons of chains connected with bridges and message passing architectures. Now we're there. So the complexity of the ecosystem has grown in a way that enables new things. But what this does, though, is it challenges builders to do a lot of the integration and make all these decisions about which parts of the stack they want to adopt. And you add RISC Zero into the mix, and now it's like, okay, we're using this bridge, we're using data on these L2s, we're using this DA provider, and now we want to tie it all together with a ZK proof. And so a lot of the work that I've been doing this year has been supporting people who are exactly trying to do these kinds of integrations and making sure that the RISC Zero stack is a smooth and easy experience that ties in well with Celestia data proofs, reading data from Ethereum, et cetera, so forth. Basically becoming as hard to be a blockchain engineer as it is to be like, a cloud backend engineer. It's like, oh my God, I've got 50 different databases to choose from. How do I pick?
Yeah, no, that makes sense.
I have one last question, Tim. What do you expect segmentation of customers that use Bonsai and customers who don't quite require, that level of throughput? What are you guys actually seeing right now in the market?
Yeah. So what's interesting about proof generation in general is that I would say actually that this year a major theme in the market is lots of ZK providers trying to provide the compute infrastructure one way or another for generating proofs. And so RISC Zero has a SaaS offering. A number of companies are talking about building decentralized prover marketplaces. There's a number of companies that work on supporting consumer hardware. RISC Zero is one of them. Aztec is another. And I think that what we're really seeing is that there's a lot of different, like basically anything that can do computation kind of wants the ability to generate a proof, at least under some circumstances. Generating proof on mobile devices, all these different kind of modalities. And so for better or worse, I think that RISC Zero is opinion is that all of those modalities make sense some of the time, and that there really isn't a one-size-fits-all. So we're seeing adoption on the Bonsai system, but there's also a lot of partners we're supporting who don't use Bonsai. They just generate the proofs on user devices or on their own servers. And that's exciting to us too. That was one of our objectives. The decentralized proving marketplace thesis is an interesting one. For users like Optimism, Tycho, Eclipse, anyone who's building like a chain, they actually do need a lot of proofs to get generated, but they don't want to be dependent on a centralized SaaS service, because what kind of blockchain is centralized, right? Like, that's supposed to be taboo. And so, you know, for those kind of use cases, the proving marketplaces start to look more attractive. But even there, everything sounds easy in the one sentence version. You know, you start going down these rabbit holes. It's like, oh crap, like, is my blockchain going to be able to pay these provers in my native token? Do I have to get another? It gets really messy. So we've been taking kind of this we don't want to race to the wrong answer kind of approach. We've been a little patient, I think, in terms of seeing what actually gets traction and what the markets finds works best, and engaging in the process that way.
Do you think the marketplace will mature in this calendar year, or do you think that's really not a 2024 actualization? There's a bunch of moving components, right, for that to be like an efficient solution.
I think that we're still going to see a lot of churn in this space over the next maybe 3 years at least. This year, there's a number of new VMs that technically already have tech demos. They're maybe not production usable yet, but it's early in the year. I would expect some of them to be, you know, fairly competitive by the end of the year. Powder will come to mind for that. Delphinius has made huge upgrades to their WASM proving system. O1 Labs has a new prover called Kimchi. So I think that this will be kind of the year of the like general purpose ZK-VM wars, if you will. We're going to have like a lot more competition in that space. And then I think I've talked to maybe at least 4 people who are funded and working on building decentralized proof marketplaces. So we're still in that, to use the evolutionary kind of metaphor, this niche is still exploring the space of solutions and hasn't converged on optimal yet. It's just going to be good news for the consumer ultimately.
Yeah, thanks, Tim.
Yes, go ahead.
I have a couple questions. The first one is, what exactly are you doing for the on-chain proof verification? Are you compiling Rust into Yule or doing something like that at all?
Great question. So there's actually 2 approaches that we've taken, and it depends on which chain we're targeting. So if you want to do the proof verification on a chain like Ethereum, there you don't want to like do any fancy Rust to Solidity type tricks or anything like that. What you actually want to do is, well, what we do anyway, is we just use a Groth16 snark. Now, how does that work? Well, our ZK framework is all Stark based, but we do have a way to verify the Stark using a Groth16 circuit. So this is called the Stark to Snark transformation. We did not invent this idea. It's a general idea. And so if you want to publish on chain, we give you a Groth16 proof, which can then be verified by, there's kind of a standard open source Groth16 verifier contract. And that's the thing that's like 270,000 gas, give or take. The downside to Groth16 is that it does require a community like setup ceremony, right? There's like some magic goo variables. This is one of these things that's like come to crypto ever since Zcash needed to do this. So we're in the process of setting all that up. So that's for the Ethereum case. We convert to a snark and then we verify the snark. Now for the COSM WASM stuff that my colleague Austin is doing, there you don't have as much pressure on compute on COSM WASM chains as you do on Ethereum, just generally speaking. And so there you can get away with taking our Rust code, compile the verifier, compiling it down to WASM, and just running it completely as is. And that's what we're doing there. Although if we wanted, we could also do the snark verification instead. So there's a few options.
Got it. Sounds good. I just saw some use cases where people would compile Rust into Yule, which is not Solidity. It's basically like a
Yeah.
Solidity assembly code. And that also allows you pretty much to have not everything, but like a lot of things that are
Pretty
possible
close.
in Rust, you can just bring
Yeah.
them on a VM.
Yeah.
And
You know,
the
one of
second
the
question that I had.
oh, go ahead.
Oh,
Sorry.
please go ahead. There's
I-
another question, different one. Yeah, go ahead.
I was just going to say, yeah. So one of the other considerations is the size of the proofs themselves. So on Ethereum, every byte of call data costs you 4 gas, and so these snark proofs that we generate, they're 900 bytes. So they're less than a kilobyte. The Stark proofs are like 200 kilobytes, and so the snark is useful both for reduced cost on the compute side for Ethereum, but then also less call data. We'll see if Cancun updates more block space or whatever changes that calculus. But yeah, I was just gonna. That's it. What was your other question?
Yeah, that makes sense. And the other question is there a feasibility for a blockchain where proof generation could be used as proof of work? Because, like Ethereum and others, they moved to staking system, but
Yeah.
and Bitcoin's still using like useless computations.
Yeah.
Is there a way to combine those?
Yes, in fact. So there's a few academic papers that explore this topic. I think that the main sort of label for it gets called proof of necessary work. And so here the idea is you set up your ZK system so that the ZK proof not only testifies to the outputs of the program, but also includes an attestation to how much work went into the prover. There's a number of metrics you could use for that. Yeah, useful proof of work, exactly. And actually, when we started the company, the original plan was, what you might call just the standard crypto cookie cutter idea, right? It's like, okay, we have a ZK VM, time to build a blockchain with it, right? And the plan there was exactly that we were going to do consensus using this proof of useful work type of idea. Of course, then FTX collapsed and a few other things in the market changed, and we said, okay, maybe we should reevaluate the strategy and focus on more fundamental value. But yeah, it's absolutely a legitimate approach, though.
Got it. Thank you so much.
Yeah, good question.
I think we're just about out of time here. But like Tim was saying, we do have a Slack channel with them, so sure we could always be in touch asynchronously on any future questions we have. Tim, thanks again so much, man, for taking the time. This was really, really interesting. If you have the slides, you could send and I could share it with the rest of the team. So
Absolutely.
we could after. Again, thanks so much for doing this and taking the time. Just for the rest of the team, we're having our next of these events next month, March 12th, I think. Yeah, March 12th with Steve Dack from Ethereum Attestation Services. So hope to see you all there. Thanks again for Tim for taking the time, and thanks for all of you guys for coming. And we'll see you then.
Thanks, Tim.
Thank you so much. It was a real pleasure.
Okay.